So we're just going to quickly review simplifying radicals and then using that to solve quadratic equations. So the main two things that we're talking about today is this property here. This is our product property. And the way that I want you to think about it is if two numbers are multiplied under one square root, we can give each number its own square root and multiply them. Same thing with the division property or our quotient rule. There's a lot of different names we might call it. If two numbers are divided under one square root, we can simply divide the numbers under their own square roots. So when we're starting to simplify, you can obviously see the directions are written here. Simplifying a square root means removing all the perfect square factors. So like showing our full work on the first one, I want to rewrite 48 as a product of two numbers, because if it's a product of two numbers, then I can split it up into two square roots. And when we're rewriting it, we want to rewrite it as a product of a perfect square and then a non-perfect square. So remember, perfect squares that simplify are like 4, 16, sorry, I skipped one, 9. So 4, 9, 16, it's 5 squared, 6 squared, 7 squared, so on and so forth. So like with 48, I know that's 16 times 3. So then if two numbers are multiplied under one square root, I can give them each their own square root, and I can multiply those products together. So the square root of 16 is 4, and then the square root of 3 is just 3. Now 3 doesn't have any perfect square factors, so that's how I know that I'm done simplifying this. There's a few things going on that I'd also comment here. We don't always show this step. It's very common just to jump to that step, which is fine. And the last thing that I would say here is we always look for the biggest perfect square factor. But if you can't find the biggest perfect square factor, it's okay just to do any perfect square factor. So for example, like if I didn't know that 16 times 3 was 48, I could have done 4 times 12. And then I would have, split that into root 4 and root 12 using the product rule. And then when I'm done, I always want to ask myself if I can go further. So like here, I knew I was done because 3 doesn't have any perfect square factors, but I know that 2 does. So I could continue in multiple steps. And then just reminding ourselves that everything is already written as a product, so everything is just going to remain a product. And then at the end, we would still get the same answer. So we can do it in multiple steps, but we know that we're done when the number under the square root doesn't have any perfect square factors anymore. So with that, I would say number 98 is the same as that, so you can just continue to work on that as your homework. Same thing with this one here. Just to quickly show like a few division things. When we have two numbers being divided under one square root, we should simplify that or rewrite that maybe as giving each of their own each number their own square root. So with that, though, it kind of brings up just this rule that we use in early algebra classes, that we can't have roots in the denominators. So that's the idea of rationalizing, which you've encountered before. So if we rationalize the denominator in this case, I want to do something at the top and the bottom that would get rid of the radical but not change the overall value. So something like root 5 over root 5, that number, if I were to simplify it, was just a 1. And anything times a 1 is that thing that we started with. So I'm not changing its value, I'm just changing how it looks. So root 5 times root 5. Now, there's two ways we can think about this. We could think about our product rule going backwards, right? If two numbers, or if two square roots are being multiplied, they could each go under one square root. So that's what we'd kind of think about first. So root 5 times root 5, I can combine them under 1. And then the same thing up here, I can combine those two individual radicals into 1. And that helps us simplify. So this is root 15, and then this is going to be root 25. So at the end, we have successfully removed the square root in the denominator. So what we're saying here, just to be clear, is that this fraction, root 3 over root 5, is the same value as this one. They're just written differently. With that, like I would just quickly look at number, the one below it, I guess. So if I see two numbers under one radical, I can give them each their own radical. And this starts to combine our simplification. Now there's two things that we could do here. I'm just kind of demonstrating both common ways. Like it might be common just to simplify the root on the bottom first. And if you did that, I need to get rid of the square root of 3 on the bottom, so I could multiply the top and the bottom by root 3. Now in this case, we get root 21, right? 7 times 3. And on the bottom, everything's just being multiplied. So I have 2 times root 3 times root 3. And the faster way we know that root 3 times root 3 is always just going to be 3. So that gives us the 6 on the bottom. And then with that root 21, I'd always want to make sure that there's no perfect square factors, and there isn't. Some people find it easier to actually rationalize the denominator first, because then you don't have to worry about coefficients. Now, if we do it that way first, it does bring up a little more simplification, like we get root 84 over 12. So then we would have to go simplify root 84, but we would get the same answer after that. And with root 84, I guess the biggest perfect square in that one, if we wanted to find it, would be 4. So it'd be root 4 times root 21 over 12, and then that'd be 2 root 21 over 12. So we could reduce the 2 and the 12 to just 1/6. So again, we get the same answer. So I'd leave that last one here. It's just the same. You can go ahead and do that. When we're performing operations that have coefficients and radicals, what I would just remind us is that everything is being multiplied. And if we're only using multiplication, right, we can clearly see that there is an explicit product written right there. But when I say 10 root 6, that means 10 times the square root of 6. And then that's being multiplied by 7 times the square root of 4. So we should just rearrange. We can rearrange the order of multiplication, right? We know that multiplication is commutative. So in other words, what we're getting at here is if you have a product with a bunch of square roots and regular coefficients, we can simply multiply the numbers together and then multiply the radicals together, and then we could simplify, right? So root 24 could be root 6 and root 4. So we got 70 times 2 times root 6. So the same thing would happen with this one below, right? So I'll leave that to you. But if I have coefficients and if everything's just being multiplied, we would rearrange those terms being multiplied and multiply the numbers with the numbers and the roots with the roots. And just remember, like if I have 2 square roots being multiplied, I can join them together under 1 square root being multiplied, and you'd be able to simplify it that way. So again, you'll finish that one on your own, just demonstrating the process. Now the next 2 examples just bring up a reminder of an important word, which is like the conjugate. Now the conjugate, what we see here is that we have a square root in the denominator. And as we said before, we're not allowed to have square roots in the denominator. We have to rationalize it. And with these examples, there's just a single term in the denominator, so it's easy to fix by multiplying by a single radical. When we have more than one term, remember the conjugate is we keep the terms. So I still have 3 root 5 on the denominator, and I have a 4. So I keep those numbers. What I change is the sign in between them. So I'm just keeping my coloring here for a second. So the sign in between them used to be positive, so then it's a negative. Now again, I can't change the value of the original fraction, so I'm multiplying it by a form of 1, so I'm not changing its value, and now we simply use the distributive property. So this kind of brings in a few things together. So I have these 2 things being multiplied, which looks a lot like what we did there. So I'd multiply the roots with the roots, and then I'd multiply the numbers with the numbers. So I would get 6 square root of 25, which we'll simplify later. Keep using my FOIL method. So this is just a number, so I can do the number times the number, which is 8, and then it had the square root of 5. And then on top here, I go with my negative 7, so it's minus 21 root 5. Again, doing integers with integers, roots with roots, and at the end, negative 7 times negative 4 is positive 28. Now, on the bottom is what we're looking for here when we use the conjugate. The whole purpose of that was to get rid of the square root on the bottom. So after we simplify, the square root should go away on the bottom. So 3 times 3 is 9. Root 5 times root 5 is root 25, which again we'll simplify. Now when I do my continued distribution, I get negative 12 root 5. Now here I have positive 4 times 3 root 5, which is a positive 12 root 5. At the end, 4 times negative 4 is negative 16. So here we can see that these 2 roots are going to cancel out. And we know that the square root of 25 is a nice even integer value, or not even, but just an integer value. So we've successfully gotten the square root on the bottom to go away. So 9, and the square root of 25 is just 5, so that's 45. And then we have this negative 16. Now on top, we'll just clean some stuff up. This is 5, right, the square root of 25. So 6 times 5 is 30. And then these are like terms, which is, again, a big idea. We can only add radicals together if they have the same radicand, right? The thing under the square root must be the same in order to add them together. So if I had -8 of these root 5s and I took away 21 more of those root 5s, I have -29 of those root 5s, and then at the end we had a positive 28. So then our final step of simplification is just combining like terms. So this integer and this integer can be combined because they're both integers. So that gives us 58. And then this is root 5. So that's like the label. Just like I couldn't add 58 to -29x, I wouldn't be able to add 58 to -29 root 5s because they're not like terms. And on the bottom, 45 minus 16 is 29. And we actually do want to simplify this. We can check for common factors. 58 and 29 are all divisible by 29. So I'm going to factor the numerator by pulling out a factor of 29. And on the bottom, I'm going to factor the numerator so I can cancel the 29. So this actually reduces to 2 minus the square root of 5. We would expect you to reduce that. So the next one's very similar, that you can just practice on your own. But the last examples for today is once we know how to work with square roots, we can use square roots to solve something. And this is the main idea. When we're using square roots to undo a square, we have to introduce a positive and a negative answer. And a lot of times we use that plus or minus thing. So like, for example, right here, if I want to undo squaring x, the square root undoes that. But I'm not sure which version of 7 was squared to get 49, because 7 squared is equal to 49, but so is -7 squared. So again, I've undone a square root. I have to introduce the plus or minus sign. You can write it like that, or you could write it as x is equal to 7, or x is equal to -7. Both of those are fine. So if we look at the next one, this is just making sure that we know that we'd have to simplify our answers when we do that. So if I want to undo this square, I use the square root. And whenever I undo a square with the square root, I don't know if it was a positive or a negative version that was originally squared, so I have to introduce that. And then we understand we always have to simplify our answers. So to simplify the square root of 80, I know that 80 is 16 times 5. So that our final x value would be plus or minus 4 root 5. So as they progress, we can use the square root method. We're talking about quadratics, so we know quadratics are always in this form. We can use the square root method if b is 0. In other words, if there's no regular like degree 1 x's, we'll always be able to solve using the square root method. So on the examples that are left, you notice that there's x squareds, but there's no x's. And the general process for those is you must isolate the x squared term first. So I have to add 11 to both sides here. So I get 3x squared is equal to 34. And then I would need to divide by 3. So I get x squared is equal to is equal to, I guess that's just 34 thirds. So then to undo the square, now I can use the square root, but again, I always have to introduce the positive and the negative versions because I don't know which one I have. Now part of simplifying is making sure that you don't have a fraction under a square root, which is also listed on the front side of the notes. As you're reading those, it's number 2. I was just verifying, it's number 2. You can't have a fraction under there. So with something like this, we would need to simplify, right? So we get plus or minus the square root of 34 over root 3, in which case we'd have to rationalize. So we get plus or minus, on the bottom, root 3 times root 3 is just 3. And on top, 34 times 3 is going to be root 104. 102, excuse me. Now I know that that's not going to simplify because 34 doesn't have any perfect square factors, and neither did 3. So when I multiply them, it won't have any perfect square factors. So I'd actually be done there. So the rest of them are very similar. So make sure you can finish those up on your own.